Farbod Shokrieh from the University of Washington. We're very happy that he's speaking for us today. And he'll be speaking about canonical local heights and Berkovich skeleta.
Yes, hi, thank you. Thank you for having me. I wish I could come to Toronto in person, maybe next time, but it's been a while since I gave a Zoom talk, so please bear with me if I have forgotten how to use technology appropriately. There will be, so when I was invited to give a talk, there was an interest about maybe some other connections to tropical geometry, and I just want to advertise that there will be some tropical stuff in the context of Berkovich spaces as well. And everything I talk about is joint work with Robin de Jong at Leiden University. So let me start by some background known functions that we learn in graduate school, maybe canonical heights. In the context of abelian varieties, one can extend it to dynamical systems, but let me set the notation. K for the talk is going to be a number field. You're welcome to think of a function field analog. And things are slightly easier for function field if you're a geometer. Oh, by the way, there's a paper on the archive with the same title as the title of this talk, if you want to look at more details. I will work with an abelian variety over K, and I will fix a symmetric divisor, symmetric effective divisor, and those assumptions can be dropped, but it's easier to work with or it's easier to present the work in the symmetric case. Symmetric effective divisor. Just a reminder, symmetric means since we have a abelian variety, you have the multiplication by -1. And if you pull back the divisor along that map, you want a divisor which is linearly equivalent to what you started with. And if you're thinking of line bundles, you get the isomorphic line bundle. Okay, to this data, there is something called canonical or Néron-Tate height, and it can be defined at many different levels, but at the level of points, I'm going to use this notation h hat of d, which you can feed in points, even geometric points, and you can get a real number. In fact, positive or non-negative real number. This is canonical or Néron-Tate height. And this is an important function. Generally, the theory of heights is useful in finiteness questions. It captures complexity of points, or if you extend it more higher dimensional objects. But in the case of abelian varieties, because we have the addition, you have an even nicer height function. So generally, heights are defined up to a constant or up to a bounded function, and you can, so Néron and Tate realized that there are tricks or methods to give a God-given canonical height function in the case of abelian varieties. So Tate, this is a still mysterious function. It's extremely useful. You have seen this in action probably in the proof of Mordell-Weil. Voito's proof of the Falting's theorem used this function, and even the more recent enhancements or improvements of Voito's proof, which gives uniform type bounds on the number of rational points on curves of genus at least 2, still deals with this canonical height function. Maybe I'll say maybe one mysterious thing is that we don't know much about, even though we use them, we don't know much about them in the sense that, for example, I think it's open or at least mysterious whenever this height is not 0, what kind of number do you get? Are they always transcendental, rational? Things like that are still quite open. Of course, when heights are 0, you get torsion points. It's a if and only if statement, but what if it's not 0? What type of numbers do you get? Anyway, those are all tangential to my talk. What I do want, I hope you have seen this. If not, you should appreciate there is such a function, and it's extremely useful. What I do want to focus on is the local version of this, which is, of course, very well known, but maybe not as well studied in a graduate sequence, maybe. But there is classical literature, and I'll give some history. So canonical noun, local height. Canonical local height. By local, I mean I want to focus at one place at a time. So if your number field is maybe rational numbers, I want to fix a prime, or maybe prime at infinity, and say something about that. So V is a place of K. Again, if you think of K as Q, by place, I mean just a prime number or infinity formal notation. And KV is the completion of K at V. So if this is a prime number, this is Q, this is p-adic numbers. But if it's prime number, Q and prime at infinity, this is the real numbers. Or maybe you can also algebraically close and talk about complex numbers or analogs of that in the p-adic setting. Néron, in already 60s, proved the following. So he basically wanted to do a local global type phenomenon. So you have this real number, which is global. And can you find local contribution to this number one prime at a time, or one place at a time? By the way, I don't monitor chat. I see that there hasn't been any questions, but if you have questions, please just unmute. I prefer if you just unmute and interrupt me. But if you would like to write it in the chat, hopefully Payman can help.
Yeah, I'll monitor the chat.
Thank you. Okay, so Néron proved there exists a unique up to a constant, up to constants. So whatever I'm gonna say, that thing plus 5 is also also an answer to what Néron was trying to find, which depends on the place and the divisor. So I had this global function that depended on the divisor. I want a local function which has a place as input as well, which goes from KV points to real numbers, but you have to remove the support of D to real numbers, which essentially the point is that if you add over all places this function, you get more or less the function that you got back. So I'll be a little bit more precise. But so he investigated these functions exist and satisfy a whole lot of things, satisfying a bunch of things. But let me just, for the purpose of this talk, I'm going to focus on a few things and maybe be vague about others. It's a continuous function. Okay, think about that. What do I even mean by continuous? And then I'll be vague about 2 and 3. Lambda of D1 plus D2. If you add two divisors, you get the summation of the functions at D1 and D2 up to a constant. Everything is defined up to a constant. And then third one, I won't write it carefully, but it's functorial with respect to isogeny. So if you have isogeny between two abelian varieties and you appropriately pull back a divisor from the right side to the left side and all that. So I'll just say functorial with respect to isogenies. And you can say a few more things, but the number 4 is essentially the why I call it local. So if you add these lambda dv's of a given point P, you essentially get up to a constant, but that constant is kind of a knowing what constant. You get, so if you add over all places. So this quotation means up to a constant. There's a universal constant which of course depend on how you normalize these things individually, because those constants will add up to another constant.
Yeah.
And this function, as you can imagine, is most of the time supposed to be 0. And this makes sense because these individual ones don't make sense for support of D. I have to say for P not in the support of D. So essentially, you can decompose this global function, global number, to local contributions. So there is an actual construction due to Tate, which is limiting. You take some kind of a limiting process, and this function, there is a natural choice for this canonical thing that fixes the constant on the right side. So the question of what to do with the constants on the left side is annoying, but it's something that we can also study and address. Okay, so that's the ancient history. By ancient, I mean 1960s. Maybe I'll say a few things about Néron's computer. So Néron didn't not only just say these things exist, and in fact, in the process of existence, he constructed this, what we now call Néron models, these minimal models of abelian varieties. I think those models became so important and useful that people have forgotten that this was his motivation, apparently. So they have their own lives at this point, but not only he said they exist, he gave formulas. He was also interested in how to compute these things, gave formulas. In various settings, various formulas. So one version of it is a limiting formula. This is similar to Tate's for limiting trick. For the global heights, which have the which you might have seen this. I mentioned earlier this process. So Tate says these canonical heights exist by showing that there is a Cauchy sequence, and then you use the fact that R is complete to say that these numbers exist. But that doesn't give a lot of information because a sequence has a limit, but we don't even know what that limit is when it's not 0. It's a mysterious number, as I was saying earlier. So this limiting formula is again an existence result, really. It's not very useful in computing things. But he did give a formula in terms of intersection theory, intersection theoretic formulas on Néron models, what we now call Néron models, these minimal models that he constructed. And I'll get back to that. And in the Archimedean case, if V is Archimedean place, he gave a formula. So what is interesting about Archimedean place, there is a rich and very classical story of uniformization of abelian varieties. So analytic abelian variety can be uniformized as some three-dimensional complex vector space modulo from full-dimensional lattice. Then there is a theory of theta functions that you can present. So there's a function theoretic way of studying sections of line bundles. So he used this beautiful uniformization theory that formulas in terms of theta functions, in terms of theta functions, classical theta functions. Okay, so that's Néron. Tate, who was influential in the global business, he also got interested in the local business, and then he said, how about these non-Archimedean? He gave formulas in the dimension 1, in the case of now what we call a Tate curve. Gave formula in terms of, again, theta function. So this is for elliptic curves. And some mysterious polynomial, which is called Bernoulli's polynomial. So as apparently was the case, he didn't publish it, and he sent the computation to various people. And I think Serre in his book Lectures on Mordell-Weil, Lang in his book Diophantine Geometry, I think, and maybe Hindi and Silverman in their Diophantine book write down this formula. And this Bernoulli polynomial is a very mysterious thing. Somehow, if you know the classical story, you expect theta functions, but this Bernoulli is a mysterious thing. So maybe now I can advertise. My talk will be sort of, I'm not giving details of these things, but my talk will be giving the context and geometry of what's going on for 2 through 4. And in particular, we extend Tate's formula to every dimension. Okay, so that's sort of a snapshot of what's to come. So our contribution, and by R I mean Robin de Jong and myself, our contribution will be, we give a concrete expression involving theta functions and Berkovich spaces. In particular, our work can be thought of, so we use the uniformization theory, similar to what Archimedean uniformization theory was. We use the non-Archimedean uniformization theory, and we give expressions in terms of theta functions. But also there is this contribution, Bernoulli type polynomial appears in our work in every dimension. So another byproduct is that we for me personally, it was satisfying to understand where this Bernoulli came from and what is higher dimensional analog of this Bernoulli thing. Okay, I think it's fair that I should not assume everybody has seen Berkovich spaces. I know they're becoming more and more popular, but I don't think, I have taught a course in University of Washington, a year-long course on Berkovich spaces, but I don't think the target audience are my students. So, and I realize there will be students and postdocs watching these videos. So let me very quickly, in like 2-3 minutes, I'm gonna say, maybe instead of what is a Berkovich space, why a Berkovich space? What's a Berkovich space? And to motivate that, I'm going to actually go with the Archimedean story and see how things evolve or change when you go to non-Archimedean side. So let's say X is a variety over C, variety or some other algebraic. You can extend these things to schemes with appropriate adjectives, but it's an algebraic object. You might look at the C points of this object. And then let's actually have a running example. Maybe X is just A1. Well, then you go here, you get as a set, the C points of A1 is just the set C. And algebraic geometry insists that there is a very important topology that you should be comfortable with, and that's Zariski topology. Okay, you can consider C with Zariski topology. Open sets will be essentially cofinite sets, Zariski topology. But if you want to do analysis or analytic considerations, this is a stupid topology to consider. Nobody teaches complex analysis using Zariski topology. You actually remember that C has this very rich topology coming from absolute values. So you change your point of view and you use the absolute value on C, and you use analytic topology. And then you can do analytic stuff. And you're not completely alienating yourself from algebra. There are so-called Gaga theorems that you can actually, even if you care about algebra, you can do analytic things and you compute whatever thing you can compute. And then there are often in good situations correspondence theorems, for example. For proper schemes, you can read essentially cohomology theories by doing the analytic version. So maybe this whole package should be considered as the analytic thing that you want to consider. And so the theory of Berkovich spaces or other approaches to non-Archimedean geometry is trying to do this, but it fails immediately. So let me just say why it fails, and then I'll say very quickly what Berkovich did, which is the type of space I work with most. So if X, I'm going to do the same thing, but now K is a non-Archimedean field. And it's a nice non-Archimedean field, maybe complete, algebraically closed, something like C we like. In the non-Archimedean world, you can start with p-adics, maybe you can algebraically close that and then complete that, and it's going to be a complete algebraically closed field, call it CP. You can try to do the same thing. You can look at your K points. It's Zariski topology. And then you still have, in the p-adic setup, you have the p-adic absolute value, or more generally non-Archimedean absolute value. And you can try to use that, but the problem is it's always totally disconnected. It's the pathology that will be forced on you no matter what K is, totally disconnected. And I think at least we should be uncomfortable with doing analysis on a totally disconnected space, and more or less, I mean, one cannot imagine this is a nice space to work, at least the classical version of analysis that we know. So maybe in the case of A1, you're looking at the picture which is just totally disconnected space. And the solution of Berkovich was, so there are various solutions. Tate, in a different work called rigid analytic geometry, had some idea that one should, this is totally disconnected because you're looking at too many open sets. Maybe you should do, instead of just usual topology, you should use Grothendieck topology. And there is a theory that works. But Berkovich's solution, which came after that, is more sort of hands-on, in my opinion. Berkovich's solution is to look at, there's a way to canonically add, so there are missing points here. There is a, so canonically, sorry, I'm using the word canonical too many times in this talk, I realize, but this is the old-fashioned canonical that mathematicians are used to. There is a natural way to add points to this. And it's so nice that will make your space very connected, and in fact, much nicer than that. It comes with structure sheaf and all that. So maybe in my example, so idea, let's say for A1, is that you should look at the ring of functions on A1, which naturally you should think of the polynomials in one variable. So this is your ring. And it's this general phenomenon that in order to understand the space, you need to understand functions on that space. So this ring is supposed to know everything about the space you want to construct. And the idea is to use points are supposed to be, I'll put quotation mark, characters of KT. Except the word character is not the right thing. The better word is semi-norms. In the Archimedean setting, these two will coincide, but more generally in the non-Archimedean setting, things are pathological, and the crucial observation of Berkovich was that semi-norms do the job. Multiplicative semi-norms that extend the absolute value on K. But I don't want to give too much details. But let me pictorially just say, so this was your attempted XN for A1. Is there a question? Sorry, I heard a noise, but. So for A1, if you do this process of looking at characters, you're going to actually get extra points. And you get all the points that I'm drawing now, all these lines that I'm drawing are kind of new things. And they didn't exist. You get some kind of a tree-like structure. It's a crazy space, so I'm not gonna finish drawing it, but it's gonna be some kind of a locally path connected. In fact, some kind of a real tree will be the analog of the complex plane over non-Archimedean fields when the field is nice enough. Okay, so that's my very quick introduction of, at least I hope you're convinced that there is a problem and there's a solution. I'm not giving you the details of the solution, but the solution is actually quite beautiful and natural, and it's compatible with many of other parts of mathematics that you're familiar with. Okay, so if you apply this machinery to a curve, which is not the focus of this talk, but I mean, I'm thinking about abelian varieties. Maybe I care about Jacobians at some point, so I need to understand what curves look like. It turns out you can actually, if I give you some time, which we don't have extra time, you can imagine what kind of space a curve should look like. Remember, a Riemann surface, which is a curve over C, locally looks like a piece of complex plane. Here in the non-Archimedean world, it should locally look like a piece of a new version of complex plane, this tree. So something that locally looks like a tree. Well, if you think about it a little bit, it's going to globally look like a graph. So it's not going to be necessarily contractible, but if you zoom in enough, it should look like some kind of a tree, which means globally might have a non-trivial topology, but. And these sort of endpoints are your classical points, the totally disconnected set that you're trying to work with, and everything else that's were created by looking at these characters is going to go inside. So these are the classical points xk, which are sort of sitting at the boundary of this picture. And then globally, you might have a graph. And these pictures are schematic, and there are too many branch points for me to draw in a finite time. And maybe more importantly for this talk, if you have a abelian variety, which is my situation, basically, if you analytify an abelian variety over complex plane, you get a so-called complex torus, C to the G modulo lambda. And here you're going to get a real torus of some dimension. So this is a real torus. And then it will have the classical points at the boundary. The picture is more than slightly misleading. So it's going to have some hairy stuff, some contractible thing going to the classical points. And then there's a real torus inside it. And in general, Berkovich spaces, there is a fantastic theorem using model theory by Hrushevsky and Dozer that proves that all Berkovich spaces in full generality have sort of topology of a finite polyhedral complex. So the fact that you get graphs and real tori is not super surprising. Any Berkovich space is kind of a combinatorial thing plus a contractible piece. One unfortunate misleading thing in my picture is that this hairy stuff are one-dimensional in my pictures, but there are 2- and 3-dimensional hairs too. So there can be like a plane contracting or something. I'm not claiming that everything going from classical points to this skeleton is a line. So it can be higher dimensional contractible things. But one thing that's true, which will come in my main theorem, is that there is a canonical way to take a classical point. So this is classical point P. There's a canonical way to bring it down to the skeleton, to the real torus. So there exists a canonical, once again, canonical retraction map. In the case of abelian varieties, which can be written down actually very concretely, which I will call it trop from A K, the classical points, to sigma, which I will call this real torus sitting inside the Berkovich space. And I will call this tropicalization map. And in fact, one way to define tropical geometry is, at least for the case of, say, abelian varieties and curves, is just the study of skeleton of Berkovich spaces. So I hope nobody gets offended by saying that tropicalization can be defined. There are various ways of defining it, and different people have different favorite way of thinking about tropicalization. But for the purpose of this talk, or tropical, maybe let's say tropical geometry, this is one definition, is the study of the skeleton. By skeleton, I mean this thing that sits inside Berkovich space. Study of skeleta of Berkovich spaces. And by no means I'm saying this is the only way of thinking. I mean, some people might very much not like this definition, but this is, for the purpose of this talk, this is the appropriate definition. So I will have tropical objects and I'll have classical number theoretic objects, and there's a map going from classical points to tropical points. Okay.
Is it possible to get a little bit more intuition about the skeletal of Berkovich spaces? How do you define them?
So there exists a real torus. So this is a theorem. There exists a real torus of dimension G prime. Let's say abelian varieties of dimension G. There exists a real torus of dimension G prime such that G prime is less than or equal to G, and the entire Berkovich space deformation retracts to that. But I can actually say, maybe now that you said it, that this is a little bit getting technical, but if you have an identification of A, in the sense of Berkovich, this is a sort of topological space. You have a universal cover, and you have fundamental group, which happens to be abelian just in the classical case. This is some kind of a real lattice, or integer Z lattice. And more or less, at least in the case of, say, principally polarized, you can think of this sigma as being the ambient vector space of this lattice modulo the lattice itself. So you get a real torus out of that. This is not trivial. I'm just saying there exists a uniformization theory, Raynaud's uniformization theory, that you can take that, and more or less this is a definition of this skeleton. But there are better definitions. There are certainly more conceptual ways, which won't fit into a 1-hour lecture. But this is, I think, good enough. In particular, if lambda is, I mean, it can happen in the non-Archimedean world that actually you don't have a useful uniformization. If you have good reduction at a prime, for example, at a place, then the skeleton is actually zero-dimensional. I said the dimension of the skeleton can drop. So this space can just be a contractible space. But when you have bad reduction, you do have this torus, and you can leverage that to actually use combinatorial arguments to give formulas, as I will do soon. Is that
yes, thank you very much. It's very helpful. Yeah. Okay.
So Farbod, the G prime somehow measures how, how bad the reduction is. How
yes.
reduction.
Yes. So G prime, if it's 0, it's good reduction. If it's full, it means it's sort of maximally degenerate reduction. And it can be in between. And what happens is that even then, Berkovich space remembers a lot, but it remembers in the sort of the structure sheaf. So all the missing topological dimensions are going to be hidden inside sort of the local field, completed local field at some points. There is a formula that actually says G prime plus a bunch of other numbers is going to always be G. And those other numbers come from the function theoretic data on the structure. The same, by the way, for the curves. In fact, the notion of Tate curve, which was the focus of the work of Tate. So you have bad reduction when the valuation of your lattice is in a particular way, you get a circle in the Berkovich space. And if not, you get a point. It's going to be, so everything sort of fits nicely into this picture. And if you're willing to think of beyond topology, but in this talk, I'll just think about topology. Other questions? Thank you.
Thank you.
Thank you. Yeah.
Okay, now I can get to the technical part of my talk and give some theorems. I'm done with the background, but the theorem is somewhat technical, but I hope I can convince you that it's the expressions are technical, but it gives some rather precise formulas for canonical local heights in terms of the geometry I was just talking about. So canonical local heights of Neron versus Berkovich skeleton. These, in the case of abelian varieties, we were talking about these real and tori. Okay, just to set notation, I'm going to have R, which is a complete DVR. And F is the fraction field. For the purpose of this talk, really, you should think of the completion of your number field at the place V. So this is like the p-adics, or p-adic numbers if you start with Q. Okay, so I have already fixed the place. I also had a divisor. So lambda function that I want to understand was the input was a divisor and a place, fix the place. I'm going to fix a section, a global section of a line bundle. L with divisor D. Okay, so in a way, I'm remembering this divisor D via fixing this section. And just like in sort of complex geometry or even manifold, you can think of line bundles together with a metric. This is a phenomenon that algebraic geometers don't do often, but if you do complex algebraic geometry, you do think about Hermitian line bundles. So I want to do sort of a metric, imposing a metric on line bundles in this new analytic situation as well. On this L, I put a so-called canonical metric, once again canonical. On L, I'm going to give an axiomatic definition of this. What is this canonical metric? So you have this multiplication by n for any n. I'm on an abelian variety. Let's pick n equal to 2. Multiplication by 2. If you pull back a symmetric, remember at the beginning I said D is symmetric. My line bundle is going to be symmetric, meaning multiplication by -1 gives you a pullback by -1 gives you isomorphic line bundle. Pulling back a line bundle with respect to multiplication by 2 is going to give you a line bundle which is 4th power. This is a general fact. In fact, there is a formula for any n. In the symmetric case, it's going to be n squared here. So 2 gave you 4. If I pull back by 3, it will be L9 and so on and so forth. So this is an algebraic isomorphism. You can say I want a metric on L such that this turns into an isometry. So you can say this is my wish, and then you can work hard to say that this wish can be realized. In fact, Gubler and Shokrieh and others have shown that such metric exists. So this exists, and this is not super trivial, but it's been worked out by people like Gubler and Zhang. And I don't remember I'm sorry, the talk is being recorded. I don't remember the exact history, but this is certainly a known fact worked out by good mathematicians.
And this is a unique metric, or
yes, this is a unique metric, and in fact, the word canonical here is actually kind of faithful to the original usage of canonical. It can be constructed using some kind of a Tate trick. You can iterate some process, and you get in the limit you get this unique metric. Okay, this is known. Now I'm going to say some really cool facts. In fact, at the beginning I said something that was good to dwell on. What do I mean by this function being continuous? So I said Néron says this function is continuous. What did he mean? Well, you have a function from a sort of a V-adic space to real numbers. You have the topology here. You have a V-adic topology here, and you insist that the topology, so open sets here should pull back to open sets here, which is a weird thing, at least in 60s, that you are comparing a map between V-adics and reals, and you insist that open sets should go back to open sets. But with this new space, Berkovich spaces, this is a very natural thing. I didn't talk about the exact way of making the topology on Berkovich spaces, but this is sort of precisely how you put topology on Berkovich spaces. You announce certain functions going to real numbers should be continuous, and that those functions are given by semi-norms, and so that sort of gives a clue that these functions lambda dv's should generalize to the entire Berkovich space, and that's the next factor I'm going to write down. Then, so I had a section, I have a metric, so I can compute the size of the section with respect to that metric, and for some reason I'm going to put a log. This gives, in fact, the function from the entire analytic space. Well, I have to remove the support of D, because whenever S is 0, logarithm is not going to be well defined. So I'm going to remove that. This gives me a function from the entire Berkovich space away from the support of D to the real numbers. And the cool fact is that this extends lambda D, is Green's function, in fact. Green's function, meaning roughly it's Laplacian. If you take appropriately its Laplacian, you get some measure that is well behaved. Is a Green's function extending lambda D. And this is this follows from the work of Chamberlois and Tuillier. Certainly, they explicitly show that such functions are Green's functions in a sense. Okay. So we are on the right track. This is saying that I had this function that I want to understand. It turns out this function, not only on the classical points, one should look at it. One can give an analytic expression on the entire Berkovich space. But that's not, I mean, this was more or less known. What we prove is the following. You have this global section that you fix for the line bundle. This gives you, I'm going to give a definition, but it gives you a function f trop. Apologies for my notation. It looks involved, but there's a reason we call it. So this is a function f trop from the skeleton, that real torus to real numbers. And I'll say very concrete things about this function in a moment, but maybe one way to very quickly define it is, okay, let me say, so this gives this function which can be described very concretely. And I will do that at least in the principally polarized case, at least in principal polarized case. I hope I will have time to follow. I'll talk about this. But for the sake of just completeness, I'm going to give a definition. It's not a good definition. It's actually a corollary of our theorems. But in fact, I said this function exists on the entire Berkovich space. If you restrict it to the skeleton, it's precisely this function. So you can define it as, it's not my favorite definition, but for the sake of completeness, I'll give you a definition. Minus log restricted to sigma. Sorry for the mess. So you look at this function that's on the entire Berkovich space, you restrict it to the skeleton, the real torus, you get some function. It's better than that. In our paper, we actually construct it in a more natural way using so-called Appel-Humbert data for the line bundle. But this is something I guess I can get away with for a talk. And now the theorem. This is with Robin there. For X that Néron cared about, this lambda d of X, the local height, which, as we saw, is log of norm of a section, is two terms. There's an intersection theoretic term, which I will come back to. And then there is a tropical term, which is this function I've been talking about. And I'll talk about a little bit more in a moment. So the pictorial explanation of what's going on here is, if you give me a point X, I'm going to bring it down using the trop map. And I get trop of X. Then I have a function on this torus, which is, apologies. So this is the picture of the tropical or Berkovich abelian variety that I had drawn before. I said there is a map, tropicalization map, that brings down classical points to this real torus. And then I said there is this map on the real torus that can give you real numbers. And the second term in this lambda d is going to be a tropical contribution. You bring it down, then you hit it with this function. And the first term is more classical, and this is intersection theory of closure of the point and thickening of the divisor on the Néron model. This is a more or less mysterious contribution that was known already at the time of Néron. The second term was this mysterious contribution that, for example, Bernoulli contribution comes in this side. I'll talk about it in a moment. So what is Néron model? I mean, I'm not going to, there's a book called Néron model, 600 pages. What I will say in one word is that if you have an abelian variety, you can extend it in a, the push forward of this thing is going to be in your Néron model. So you have a map from spec K to spec R. Did I call them K and R? No, I called them R and F. Sorry, this was F. So I had this complete DVR. F was my p-adic field. If you have a abelian variety over F, you can look at the so the fact that this push forward exists is the theorem of Néron, and for abelian varieties, such things exist. So if you have a point here and a divisor here, you can extend them to the model, and you have intersection theoretic contribution there. And we are saying that this local canonical height is that intersection theory plus something very tropical. Okay. I must admit this second term is quite mysterious. I hope you understand there exists a function and there exists this tropicalization map. And the question is, can this, I mean, once you know what this function is, you can imagine this is a very concrete computation. So let me tell you, in the principal polarized case, this function is super concrete. And in fact, this is the general form of Bernoulli contribution. So let me say principal polarization case. What is this mysterious function I'm talking about? Remember, we have this real torus. So skeleton is this real torus, which in passing, because of Jan's question, I actually said this is sort of the fundamental group of the Berkovich space, ambient vector space divided by the fundamental group. It turns out the principal polarization, and in general, any polarization gives you a map, gives the analog of Riemann form, gives you some kind of a symmetric function on this lattice. In fact, on the vector space, you can extend it. So the information of the polarization gives you a bilinear form on this lattice. So what am I talking about? You have this lattice. I'm thinking of my real torus as the paper modulo this lattice. And then I'm saying I have an inner product on this space. And this inner product comes from the polarization data. Okay, so the second theorem, again with Robin de Jong, says that essentially this F trop, which up to now I've just claimed it exists, but it's essentially closest lattice point, closest lattice point function. What does that mean? If you give me a point on this vector space, the universal cover, I can look at what is the closest dot to it, closest lattice point to it. So in this picture, maybe that point is the closest, and I will record the distance to that closest lattice point. And for some reason, I record square of that distance. So I record, so this is minimum lambda in lambda C minus lambda Z minus lambda, the norm squared of.
In this closest point will be uniquely determined, or can it be more points which are equidistant?
It can be, but I remember just the distance. If there are two, like if you are in the center of this triangle, maybe all three of them are in the same distance. You just remember the number or square of that number. And this is something that people actually studied in optimization for like quantization. You have a data which is in a vector space, but then there are some permissible outputs which is this lattice, and you always want to quantize it, go to the closest lattice point, and you study the behavior of this function to see what are your error each time you quantize. So this is kind of a classical thing that for other reasons people must have looked at. And when I said it's essentially equal, it's up to a shift and a console. Let's call this function, for some reason, this had appeared also in my earlier work with Robin in a number theoretic setup again. But the actual theorem says that there exists a shift and a constant. So f trop, a more accurate version of it is that there exists some kappa and some r such that this is this closest lattice point function up to a translation plus some real number. So there's a translation and some shift involved, but those things can be worked out as well. But more or less, this f trop is this function. But now, this function is a quadratic function, right? It's just self-product of some bilinear form. And the Bernoulli is also a quadratic function. So let me just end by saying that this explains Tate computation. So the last thing I wanted to say, Tate curve. If you work this out, you get what Tate had computed. Let me write his formula and then I'm wrapping up. So this Bernoulli polynomial, this is Bernoulli, is essentially a quadratic function, B2 of t, up to a shift and a constant is a quadratic function. So this is a quadratic function up to a shift and additive constant. And I want to advocate, and we justify in our paper, that this is really the contribution coming from f trop of the tropicalization. Here, okay, Z is the, so AN is uniformized this way, and Z is the a lift of, so X, if X is here, you can pick Z here that descends to that. Q is the lattice, the lattice that you're modding out by has a generator Q, and yeah, this is the non-Archimedean theta function, which anyway, in the last chapter in our paper, we show that this our formula extends precisely Tate's formula. And then maybe one last comment, I apologize, local, global. You can add our lambda x's and you get a height. And you can ask what is the relationship with the Tate's height. There's a constant issue here. If we insist that lambda d, it's integral over Berkovich space, is 0, that's a way to fix our constant, then right-hand side and left-hand side are equal up to some concrete term that we call Néron-Tate height of theta. Okay, so that was quick. What I'm saying is that our geometric point of view using Berkovich spaces gives us a way to normalize these local heights such that we can handle the summation formula, the constant involved in the summation formula, and we can say precisely what that constant is. Okay, so that's all I wanted to say. Thank you for your attention.
Thank you.
This was a very, very interesting talk, fascinating work. I will look more closely to this